Hi, everybody. So my name is Eylon Shamir. I'm the chief scientist at the Hydrologic Research Center. And I'm going to talk today about the operational flash flood early warning with national coverage and the global initiative focusing on Europe. So HRC, Hydrologic Research Center, we were founded in 1993 as a non-for-profit research, technology transfer, and training organization. And our objectives are to bridge scientific research and applied solutions to address critical water-related societal challenges. So we are talking today about flash floods, and just to set the floor and to make sure we all talk about the same thing. So a flash flood, based on WMO's definition, is a rapid onset flood occurring within a few hours, typically less than 6 hours, of the causative rainfall or other triggering event, characterized by high flow velocities, relatively high peak discharge, and limited warning time. So small floods that occurs in small basins are among the most destructive weather-related hazard worldwide. Many peoples in flash flood-prone regions with little or no warning capability. Greatest impacts are often borne by developing or least developed countries with limited forecasting and early warning resources. Little in situ data in small basins. So most of the instruments are used for large rivers and not in small watersheds. And large river flood warning strategies are ineffective for flash floods. So this is more of a hydrometeorological phenomena, and kind of traditional hydrology sometimes does not is not effective for flash floods warnings. So following the 98 devastating Hurricane Mitch in Central America, we, HRC, developed the first regional flash flood warning system, and it was deployed in Central America in 2004. In 2008, there was a memorandum of understanding that was signed between the NOAA, USAID, WMO, and HRC as the technical development, and the idea was to implement this flash flood with a global coverage. Flash flood guidance systems is a global coverage. And the primary objective was to reduce loss of life and property from flash floods worldwide, particularly in data-sparse regions, by strengthening national hydrological and meteorological forecasters' capacity to develop location-specific, actionable early warning and watches for flash floods. So as of today, or as of the end of 2026, we will have the end of, we have now developing 2 new regions, and we will have 16 regional and national systems covering more than 80 countries and provide early warnings for more than 40% of the global populations. So since we are focusing on Europe, in Europe we have one system in Southeast Europe that covers Albania, Bosnia, Herzegovina, Croatia, Montenegro, North Macedonia, Moldova, Romania, and Serbia. So we also have, I know that the Middle East is not connected in any place, is not covered by Asia and maybe covered partly by Europe. But we have a Black Sea Middle East system that covers Armenia, Bulgaria, Azerbaijan, Georgia, Iraq, Israel, Jordan, the Palestinian Authority, Lebanon, Syria, and Turkey. It is hosted, both systems are hosted in the Turkish Meteorological Service. It's TSMS, and I forget the acronym, but it's the Turkish Meteorological Service in Ankara. So both servers are hosted there, and they provide information that is password protected to the national hydrological and meteorological agencies of all these countries. These are 2 separate systems. So what is the flash flood guidance system? So here you can see a nice interface that we have that have all um, the most of the products together. It's an operational system that provides national and hydrologic and meteorological forecasters with diagnostic and prognostic quality control hydrometeorological information to assist their development of timely and location-specific actionable flash flood warnings. And it's basically taking remotely sensed rainfall, quality controlled, together with in situ gauges to develop mean aerial precipitation in small basins. And the entire regions are delineated at a resolution of about 25 to 50 square kilometers basins. Here, this is the Southeast Europe system, and you can see that we have also radar from some of the countries. We used to get radars from Romania, but now we get 4 radars from Croatia. So we use the radar wherever we can. We have satellite information from 2 sources. This is the global hydro estimator, which was terminated. So this plot is a bit old. We still have some, we still generate pseudo global hydro estimator to keep systems that are not yet updated running. But we do use the scamper, which I'll talk a little bit more about the scamper precipitation product later. Here we get all the gauge information that we can get, and we develop mean aerial precipitation from the gauges, and we combine both the remotely sensed data and the gauge data into what we call merged mean aerial precipitation, and that's the best estimate that we can get for precipitation, and it's used as input to a hydrologic model that you can see here. This is the antecedents moisture conditions, basically soil moisture calculated by a continuous hydrologic model that, by the way, the vertical axis is time intervals. So this is 6 hours. So every 6 hours we update the soil moisture using input from the rainfall for all the basins. And this product that is, I guess, the key that is that we simulate from the soil moisture is what we call the flash flood guidance. And the flash flood guidance is the amount of rain in a given duration, either 1 hour, 3 hours, or 6 hours, that is needed to cause a minor flood in the outlet of each of the basins. So these are values of precipitation, how much rain is needed to cause minor flooding in the outlet of each of the basins. We also simulate snow water equivalent, which I guess is very relevant in Europe. So we all keep track of the snowpack. We use also satellite to get the snow cover. So you can see here in the lower right box the snow products that are being simulated. So the flash flood guidance is then, so this is all diagnostic, and then we have prognostic components, and we get as many numerical weather prediction high resolutions that are developed by the countries or provided operationally from the countries, and we compare the quantitative precipitation forecast to the flash flood guidance. And in cases in which the forecast is larger than exceeds the amount of the flash flood guidance, we get what we call a flash flood threats. Here you can see in the European system, we get forecasts from 4 different sources. We get 3 of them are from the Turkish Met Service. So again, this is the flash flood guidance. It's meaning how much rainfall is needed. We compare it to the forecast, the appropriate forecast at this time, and the appropriate time intervals. And here you can see a case in which the forecast exceeded the flash flood guidance, and therefore the system indicates that there is a risk of flash floods in these locations, and that should alert forecasters to these locations, and they should further investigate if this warranted. This is warranted of warning to be issued. So this is what we call flash flood threats. So I guess our main product precipitation is what we call the self-calibrating multivariate precipitation retrieval algorithm. It is a 2x2 real-time precipitation product available from NOAA NESDIS. It's a 10-minute rainfall intensity that has a latency of 10 to 15 minutes latency. Recently, we also started using in some of the systems the HSAF, the Italian or the European similar version of this product. This is basically infrared top of the clouds measurements from 5 geostationary satellite, the two GOES American ones, the Himovari 8 and the Meteosat 8 and 11, which are probably the ones that provides data to the European systems. So it is an algorithm that is dynamically being calibrated as information from passive microwave sensor is being available, and these are information from the GPM constellations that provide estimates usually twice per day in a given locations. But the focus here is that this is a high resolution, relatively very high resolution that is appropriate for flash floods of 2 by 2 kilometers, 10 minutes update, and very short latency. So that's a great features of this product. So this precipitation, we do have a quality control procedures that includes initial quality control of identifying anomalies. And then we have two bias adjustment procedures. One is climatological, in which we look at historical records of the satellite information and gauges and compare and do a bias probability matching procedure to have the satellite information look more like the cumulative distribution of the gauge. And you can see here the plots in the red now looks more like the adjusted blue, which looks like that follows very nicely the black, which is the gauge cumulative distribution. We also have a real-time dynamic bias adjustment procedure to adjust the precipitation using real-time gauge reports. That is done using a Kalman filter, in which whenever we have enough reports of reporting rainfall, we activate and engage this bias adjustment to correct or to bias adjust the precipitation fields of the satellites for a given region. So I guess I want to talk a little bit more on the program. This was a program supported by WMO. Now we get a little bit less support, but nevertheless, we had two very large meetings of users, one in Antalya in 2019, and the most recent one was in 2023 in North Macedonia. We had more than 200 users and participants from 72 countries, and it was a very engaged and active meeting. It was sharing lots of information and trainings sessions, and you can see in the pictures the smiling faces, so it's an indication of success maybe. And we also have lots of training, so there is a lot of technology transfer activities. There is an e-learning portal. There was in-person training. There was a certificate program in which forecasters became trainers for regional trainers, and here you can see a group of trainees from Fiji that just completed their certificate. This is a WMO certified certificate in which allowed them to go to other countries or other places to train other users on the systems and how to use it. So that's it. I have few lessons learned here from more than 20 years of operation. So as I said, or maybe I forgot to say, but this system was first implemented in 2004, so more than 22 years. And over the years, we collected lots of lesson learned, and here are some pointers in which we try to correct over the years and try to improve the system to be more user-friendly and support the work of the forecasters in issuing flash flood warnings. So I think that's the last slide that I have. And this is our team in San Diego.